confident on that.
Any questions from last time? Okay, so last time, and so last time we actually refined this, we made it better. So the last thing we showed is really, if you want, well, actually, we didn't exactly show this. We showed that the nil radical. That's what we actually showed. The nil radical, radical zero, is the intersection. We already knew this from time immemorial. We showed that we could actually sort of shade this intersection down a little bit by only considering the G-ideals. So the nil radical is the intersection of the G-ideals. And what I was trying to write up there, got ahead of myself here, is here's a statement that's a little bit more general and will not be a surprise, I don't think, to any of you. Proposition. An ideal and R is a G ideal. Oh, I'm sorry. Proposition. This is one I wanted first. Oh, it is. R is commutative identity. I is an ideal. This we knew before, but here's the new part. That is to say, the radical of I is the intersection of all G ideals that contain I. So just like in what we did last time, we can generalize this to a more general ideal. So the radical of any ideal, just consider the primes that are G ideals. Okay. Now, here is a cool characterization. G-ideals. This is actually kind of a fun one. Prove. I and R an ideal. This is proper. Then I is a G ideal. If and only if I is the contraction of a maximal ideal That is to say, so there exists, in max spec Rx such that M intersect R. That's what I mean by the contraction of this. So this is a neato characterization of the G-ideal. That is to say, it's a G-ideal if and only if there's a maximal ideal that when you maximal ideal polynomial ring, when you intersect it back down to the coefficient ring, it's equal to I, right? Let me point out that, of course, any maximal ideal is prime, and so notice that I is automatically prime, right? It's the contraction of a maximal ideal or even a prime ideal in Rx. Okay, so let's prove this. Suppose there exists a maximal ideal M in Rx such that M contracts to I. So what we want to do, of course, is show that I is a G-ideal. What we already know is I is prime, right? Because it is the contraction of a maximal, it's a prime ideal. So that is a prime ideal. And so well, I put this for emphasis here. So of course, since I is prime, R mod I must be a domain, so this polynomial ring is too. So now consider the maximal ideal. And so just let me also remind you that this is isomorphic to Rx mod Ix. Notice that the image of M is a maximal ideal in R mod Ix. Now let me be a little bit careful. Notice that M contracts to I down here. So that means that the ideal M, this maximal ideal, whatever it contains, it has to contain everything in I. So it has all the constants of I in it. So in particular, M contains Ix. So this makes sense because Ix is actually contained in M. And of course, by our correspondence theorem, M mod Ix, since M is a maximal ideal of Rx, then M mod Ix is maximal ideal of the quotient, which is isomorphic to R mod Ix. And notice that M mod Ix intersect R mod I has to be 0, right? Because basically these are all the constants that are in M by the fact that M contracts to I. And so I is a GI. Now, on the other hand, let's take it the other way. Let us suppose that I is a G ideal. Then I is prime. This was, of course, contained in the very definition of G ideal. G ideal has to be prime in the first place. And R mod I is a G domain. So in Rx mod Ix, there is necessarily a there is a maximal ideal and of course if it's a maximal ideal of this thing, it's necessarily a form, it must be a form M mod Ix, where again, this is the correspondence theorem. It must be of this form, such that M mod Ix intersect R mod I0. And so, since X is contained in M, and we know this is the case because of this, then the set I must be in M, and M mod Ix intersect R mod I is 0, it must be the case that M must be I. Because this shows that the contraction has to be at least I, and this intersection shows that it can be no more than that. Okay, any questions on that? So this is kind of a nice characterization because G ideals are precisely the ones that can be contracted from some maximal ideal of polynomials. Okay. So here it is. In the next theorem, we're going to see things that start to look like, again, sort of morphing into polynomials. This first theorem is going to show us sort of what maximal ideals look like in Rx. There. Let n be a maximal ideal of Rx, and suppose M intersect R is n. And let's suppose the contraction down to R is what we call N. Then, this is kind of a cool one. Then M, the maximal ideal in Rx can be generated by N and one more element. That is to say, so let me write it in this form. So I can generate the maximal ideal that contracts down to N by the elements of N, just use that to generate over the polynomial ring, and one more F. One more rogue element. And additionally, you can select M to be a monic polynomial. So we can select F to be a monic polynomial, which maps mod N onto an irreducible polynomial. Yeah. And chosen the monic polynomial. Um, maps to the irreducible polynomial. That bar over R mod. Oh, you know what? I think I've got it. Yes. This has to be field, so this has to be, this is an important thing that I left out. So the important thing is it has to contract to a maximal ideal in R, because I need this to be a field. Okay, so let's recapture here. Suppose that you have a maximal ideal of your polynomial ring Rx, and suppose that its contraction is also maximal in R. Then you could generate M by the elements of this maximal ideal and one more element, F, where F can be chosen to be monic, which maps to the irreducible polynomial F over R mod N. So just to clarify this. Let's say it goes from Rx to R mod N X, where F goes to F bar. So this is the standard method, I think, where you, basically what you do is you reduce all the coefficients of that mod N. Okay, any questions before we for the proof? The proof of this, despite all the words, is fairly simple, actually. By the way, so this does sound rather complicated, but how can we do this? let's get warmed up here. All right. See what you do here. And this G-ideal. It's making it too complicated. Oh. Model the whole thing by whatever that maximal ideal is. And so this allows us to reduce the easier case n equals 0, right? I'll let you kind of check the details on this, but I mean, when you mod out, you're just passing to the quotient. And basically now you're generating m by 0 with one other element, right? So let's see what happens in the 0 case. So in the 0 case, we have that m intersect r is equal to 0, right? And so what does that mean? Okay, so n equals 0, then, and I'm using the notation here for m. Right? And so what does that mean? What can we gather from this?
R is a G-idea, R is a field.
Well, so this means that, so 0 is a G-ideal, right? And so what can we include in that? R is the G domain. Okay. Right, so this allows us to reduce to this very quickly. Actually, we could have done this from an earlier one. So let's take it on from here. So what do we want to show here? We want to show that m can be generated by n and one more element. So how do we do this?
Why are you assuming n is 0?
Well, because if I don't, what I can do is original, right? So in other words, we take our whole setup, right? We have m in Rx. M intersect R is n. Now we pass to this. Right. And so passing down here to this, we do the problem. So now what we have is n equals 0, right? Because, what we have now is my new m right here is what I call m mod nx. It's an ideal of r mod nx, and my intersection is now 0. You establish it right here and just pull it back, right? Because what we're eventually gonna do is we have to show that this thing can be generated by n and one more element. Well, if it can in this case, if I can generate this thing by n and one more element, you just pull it back and show that the original one can be as well. Yes.
So if we reduce to where n is 0 and n is a maximal ideal, that means that R is a field.
Right, that's correct.
And then Rx is a PID, so the maximal ideals of a PID are just generated by irreducibles. That's where we get our F, right?
That's exactly right. That's exactly right. But I want to make sure, Eric, are you okay on that?
Sure.
Well, let's get through the 0 first, and then we'll kind of revisit. Okay, so R is a G domain, and in fact, as 0 is maximal, right up here, right? So Rx is a PID, right? And so any maximal is generated by an irreducible polynomial. And you can select this polynomial to be monic if you like, right? Because again, we're over a field, right? And so you can divide out by the leading coefficient if you like. So, and there you go, right? This is basically the statement. N can be generated by n, and if there's one more element, and we've shown that we can pick it this way. Okay. Now, how do we bootstrap it back to the original one? Now that we've done the 0 case, right? All we have to do is, this is really, if you like, so this thing right here is generated by 0f. And all you need are all the coefficients of it, or all you need are all the n's to generate this. So you can pull it back. That's essentially it.
Guess we just choose any F that maps onto.
Yes, yeah, you'll have a lot of freedom there. In fact, you probably have a lot of freedom even under the irreducibility criteria. Okay. Okay, any questions? Okay, let me up the voltage here. So what do we have? We have so M is a polynomial ideal or an ideal in the polynomial ring contracts the maximal ideal n generated by one element. And if R mod n, well, we know that's a field, right? What happens if I pretend I'm an algebraic geometer and turn up the voltage here and say, okay, R mod n is not just field, it's algebraically closed. How does that improve our little journey along the way?
The irreducible has degree 1.
That is correct. Back here, we have Rx as PID. Well, right, this one, R was 9. So when we have R mod n in general, R mod nx is a PID. If that's an algebraically closed field, then any irreducible polynomial that's monic is in the form x minus alpha, right? Because over an algebraically closed field, a polynomial is irreducible if and only if its degree is 1. You can assume that polynomial is monic, and this gives us the following observation. Here. There. We'll assume, skip anything. We assume the hypotheses is 4, 3, 12. Suppose, in addition to hypotheses, of 4 through 12, we have that R mod n is algebraically closed. Suppose we also have that. Then in fact, my row polynomial can be chosen to be the form x minus a or some a. And this is immediate from the other one by the conversation we just had, because over an algebraically closed field, this animal here has to be linear. And so if it's monic, it takes on that form right there. Okay. Let me make the following observation. So let me motivate the following definition. If R is unit ring with 1 and M is a maximal ideal of R, then M is a G ideal. Right? This was fairly easy to see, right? Because if you mod out my a maximal ideal, what do you get? You get a field, and that's clearly a G domain in a trivial sense, right? So what kind of rings do the if and only if, and this allows us to make the following definition. Um, 3.14. We say R is a Hilbert ring sometimes this is called a Jacobson ring. I don't know, historical. There must have been some feud or something. If every G ideal is maximal. Okay, so this is what it means to be a Hilbert ring. We know that every maximal ideal is a G ideal. Converse holds every G ideal like maximal ideal. Then we call this a Hilbert. Okay. Anybody give me an example of a ring that is not Hilbert ring?
Right?
What's that now?
Right? Because every prime is one. No. Those are. Yes.
Well, the integers is a Hilbert ring, for example, right? But you're on the right track. Your PID, the statement PID is a little too general. Uh, I would tend to not any polynomial ring. Well, yeah, I want one that's not one, right? That's what I wanted. I want something that's not a Hilbert ring. Basically, what you're going to need is something that's one dimensional, but still a G domain. That's probably the best way to put it. PID is the right track, but the counterexample I gave you is the integers, right? The integers isn't a Hilbert ring because, I'm sorry, the integers is a Hilbert ring because what are the possibilities for G ideals in the integers? Well, they got to be prime in the first place, right? And zero is the only one that's not maximal, but zero is not a G ideal because the integers themselves is not a G domain.
So we can localize that like three.
So that's right.
So discrete evaluation.
So I'm picking on you. For a number theorist, that would be the right answer. There's a bit of kind of, what do you mean by discrete valuation domain? A lot of people that do number theory, algebraic geometry, things like that will say that means value group Z. So that means a Noetherian valuation domain. And that's the way I always describe it. More generally, when you're talking about dimension theory, things like this, a discrete valuation domain can mean a valuation domain that has finitely many copies of Z ordered lexicographically as the value group. So they can be of any finite dimension, right? And only the one-dimensional ones are Noetherian. So I find the terminology Noetherian valuation domain to be more descriptive. But actually, let's see, to be a G domain, you just need to, yeah, any discrete valuation, Noetherian or not, will work, right? Not every valuation domain is basically what you have to do is you have to have height one prime. So if you have any valuation domain that has a height one prime, that'll work. But so let me give you one that is that's not. So here's something easy. So that's my easiest valuation domain. So this thing right here has prime ideals. There's only two of them. X is 0, right? Now, X is certainly a G ideal because when you mod out by this, you get F field. But as it stands right away, it's already a G domain. So 0 is also, it's a non-maximal G ideal. And this is a G domain because all you have to do is invert the X and you've got the quotient. Right. So, okay, so this is what it means to be a Hilbert ring, something not like this, where the G ideals are precisely maximal. Okay, so here is something that I seem to have avoided so far, but it's an important. We're going to need this, and it's important in a lot of contexts in commutative algebra. This is called prime avoidance. Yeah, see what I did with that? Okay, so here's what prime avoidance tells us. If you have n prime ideals, yeah, are uniforming with one. If P1, P2, Pn are prime ideals, and I didn't say this, but let me say this are distinct prime ideals, and I is contained in the union of these prime ideals. Then I is contained in EI for some. So if you have an ideal and you can cover it up, imagine that these prime ideals are like little quilts that you lay over the ideal I. If you can cover the ideal in finitely many of these little prime quilts, you had to have covered it by one. Almost sounds like compactness, doesn't it? Okay. So I wonder how. Well, I'll get started. Proof. We'll go by induction on N. I suspect you guys will relieve me of my responsibility to do case n equals 1, right? That one is just straightforward. So For all K. Now suppose. For all one K and N. Well, I don't suppose that. Note that for all, else, if you look at K and you take away the union of I not equal to K, PI, this thing must be non-empty. So in other words, if you take any of these primes and you pull out everything that's in at least one of the other primes, distinct from K, this must be non-empty. If not, then for some K, let's say K, and that means that PK is contained in that union. Right. And hence I is contained in that union. Oops. And we're done by induction. Right. Because we've reduced the number of primes, or the number of primes in the union of which I lies. Right. So for each K, we select something that's in, get this right. We select XK that lives in PK minus that. Union intersect. Now, the thing that you might worry about is, what happens if it's not an I, but again, we can, do an inductive argument. If this is, empty, then I must be contained in that smaller union of PI, and again, we can appeal to induction. So, this is probably a good juncture to leave it. We'll review this a little bit next time and pick it up. There's two cases to consider. One of them's easier, and that is the case when there's two ideals, prime ideals. And then it's not too much of a difference to step it up to higher than two ideals, but we have to do just a little kind of product, right? Okay, any questions? Questions on that? All right. Well, I'll